Hey everyone, this is Chapter 8 review video. In this video, we're going to go over momentum and impulse and how they're related, the law of conservation of momentum, and how to use it for collisions. First, momentum. An object in motion has momentum. The momentum P is defined as the mass times the velocity, so this is a vector quantity. The SI unit for momentum is kilograms times meters per second. Let's look at an example. A 5-kilogram ball is moving at 5 meters per second. What is the ball's momentum? Notice that the ball is moving to the left. When you are calculating momentum, direction matters. You've got to define this velocity as being negative. So the momentum is going to equal the mass, which is 5, times the velocity, which is negative 5 meters per second. That's going to give us negative 25 kilograms times meters per second. So always pay attention to the direction when calculating momentum. Next is impulse. Apply force for a certain amount of time to exert an impulse on an object. The impulse I is given by the force multiplied by the time. So this is also a vector quantity. The SI unit is going to be newtons times seconds. Let's look at an example. A force of 20 newtons acts on a ball for 0.1 seconds. What is the magnitude of the impulse delivered to the ball? So all we have to do is multiply the force and the time. So 20 times 0.1. That's going to give us 2 newtons per second. It was asking for the magnitude of the impulse, so we don't have to worry about a direction. Next is the impulse momentum theorem. It says that an impulse is going to cause a change in momentum. So I, the impulse, equals delta P, the change in momentum. We usually rewrite this equation as force times time for the impulse and mv final minus mv initial for the change in momentum. Let's look at an example. Ball A on the left here, it bounces back, so it's hitting this brick and bouncing back. But ball B just stops when it hits the brick. Which ball has a better chance of knocking the brick over? The ball that has a better chance of knocking the brick over is delivering a greater impulse, which means it has a greater change in momentum. So let's take a look at the impulse momentum theorem. Let's write the impulse equals the change in momentum, and let's write down what we know for each one. Let's call the speed of the ball v. That means that vi is going to equal v for ball A. And then Vf, assuming it bounces back with the same speed, but in the opposite direction, that means Vf equals negative v. For ball B, Vi is going to equal v, however, the Vf is going to equal 0. So even without plugging in these numbers, we can see, or these values, we can see that ball A is going to have a greater change in momentum because there's a change in momentum when it stops, and then another change in momentum when it bounces back, while ball B only has that change in momentum when it stops. But to practice plugging in the values, we can say that the momentum for ball A here is going to equal m times negative v minus m times v. That's going to give us negative 2 mv, while for ball B, the mvf is going to be 0, so the impulse is just going to equal negative mv. So we can see that ball A has twice the change in momentum and twice the impulse, so it has a greater chance of knocking the ball over. Next is the law of conservation of momentum. It states that in an isolated system, when there's no net external force, the initial momentum is going to equal the final momentum. We can write this as the initial momentum of the first object and that of the second object equals the sum of the momentum of the first object and that of the second object after the collision. Let's look at a question. Is momentum conserved when a cue ball collides with other billiard balls? So the answer is yes. When that ball is colliding, all the forces are internal to the system. We ignore any friction on the table. There's no external force during that collision. So the takeaway message is that momentum is going to be conserved for all collisions or explosions that we deal with. Whenever objects are coming together or coming apart, we can use the law of conservation of momentum. So let's look at different scenarios, different collisions, and see if we can identify what types of collision they are and which equation is going to use. The first scenario is two cars collide and stick together. Notice I've labeled the different velocities, the initial velocity of each one and the final velocity of the combination. When they stick together, it's going to be called a perfectly inelastic collision. We're going to use conservation of momentum, but for the final velocity, we can factor it out because it's the same for both. So this is what the equation looks like for perfectly inelastic collisions. Is momentum conserved? Yes, we said it's conserved for all collisions. Is mechanical energy conserved? No. When you have an inelastic collision, we have energy transformed to other forms such as heat and sound, so mechanical energy is not conserved. Just think about the car and how it's going to have deformations, and that tells you that the energy is not conserved. Another scenario here is two cars collide and go off in opposite directions. Just because they're going off in opposite directions doesn't mean that this is an elastic collision. It's still an inelastic collision. We know that there's going to be some deformation. So the equation that we can use to solve for this one would just be the regular conservation of momentum equation. Momentum is conserved, but energy is not. So for all of these, you would just plug in your givens and solve for your unknown. And then the third scenario here is two billiard balls are colliding. So they're going off in opposite directions. We're going to approximate this as an elastic collision because there's very little energy lost during the collision, very little deformation or sound created. For this collision, we can use this regular conservation of momentum equation, but we can also use this shortcut equation, which doesn't rely on mass, so it's a little bit easier to use. Momentum is conserved and energy is conserved for this collision. Let's look at an example. A cart moving at speed v sticks to an identical car at rest. Find the final velocity. We're going to identify this as a perfectly inelastic collision because the objects are sticking together. The first thing we want to do is write down our givens. We have two carts, so two masses. We'll say that the mass is m, so both masses m1 and m2 are going to equal m. The initial velocity of the first mass is going to be v. We don't know the direction, so we're just going to assume that it's moving to the right. v2 initial is going to be 0 because the second car is initially at rest. We're looking for the final velocity. So we're going to write down the conservation of momentum equation. We're going to cross out any terms that are 0, which is the second term here for the momentum, and then we can solve for the final velocity. It's going to equal m1 v1 initial over m1 plus m2. Now we can plug in our variables, m times v over m plus m. So that's going to equal mv over 2m. The m's are going to cancel out and we're going to get v over 2. So the combination of the carts are going to move at half of the velocity of the cart that was initially moving. Next, let's look at two-dimensional collisions. If you have a 2D collision, you want to separate the x and the y directions. What that means is you want to write down your givens separately for the x and the y directions. That means you can define up to 4 variables for the x direction and up to 4 variables for the y directions. If the objects don't stick together, that's a total of 8 variables. Once you've defined all of your variables, then you're going to write down the conservation of momentum equation separately in both directions. Write down what you know for each one, cancel out the terms equal to 0, and solve for your unknown. As you can see in this picture, the initial velocity for m1, for example, would just be v1 initial, whatever that speed is, but it would not have a velocity in the y direction, so that would be 0. And then for the final velocities, you can see that we have some angles. So when you're trying to find the components of the velocities, make sure to use the relevant trig functions. Let's look at an example. A 2 kilogram cart moves east at 3 meters per second. It collides and sticks to a 2 kilogram cart moving south at 4 meters per second. Let's draw a picture. the first cart is going to be cart 1, it's moving to the east. And then the second cart is going to be cart 2 and it's moving south. They're going to collide and stick together and move off in some direction. So what we want to do is we want to write down the givens. Let's define our masses. Both are 2 kilograms, m1 and m2. Then our velocities separately in the x and the y direction. So v1 initial x is going to be 3 meters per second because that's the speed and it's all in the x direction. That means that v1 initial y will be 0 because it's not moving in the y direction. v2 initial x is going to be 0 because ball 2 is moving south. It's moving south at 4 meters per second. Pay attention to direction because it's going south. That's going to be a negative velocity. We're looking for the x and y components of the final velocity so that we can find a final speed. Now we can go ahead and write down the conservation of momentum equation separately in the x and y directions. Since the objects are sticking together, we can factor out the vfx and the vfy. Let's go ahead and cross out terms that are equal to 0. Since v2 initial x is 0, that whole momentum term is 0. We can solve for vfx. It's going to equal m1 v1 initial x over m1 plus m2. Let's go ahead and plug in our values. It's going to be 2 times 3 over 2 plus 2, 6 over 4. That equals 1.5 meters per second. Now let's look at the y direction. v1 initial y is 0, so the first term is 0. Let's solve for v final y, which is going to be m2 v2 initial y over m1 plus m2. Plug in our values. We're going to have 2 times negative 4 over 2 plus 2. That's going to give us negative 2 meters per second. So that's the x and y components of the final velocity. Let's go ahead and draw these components. We have a component going to the right, so it's because it's positive, that's vfx, and a component going down because it's negative. We draw them tip to tail so that we can see the way the final velocity is going, which is exactly the way that we expected in our initial drawing. Since we're looking for the final speed of the carts, we can just find the magnitude of this velocity by using the Pythagorean theorem. Vf equals square root of vfx squared plus vfy squared. We're going to plug in the square root of 1.5 squared plus the square root of negative 2 squared. And we're going to get 2.5 meters per second as the final speed of the combination. Keep in mind that if one of the carts was moving at an angle, let's say cart number 2 was moving this way, when we were defining the initial velocity components, we would have had to find the x and the y components of that velocity. It's just for this example, we didn't have any angles, so the components were easier to find. That is it for this video.